Welcome to our webinar. I'm Rie Vinggard. I'm a professor in molecular toxicology at the Technical University of Denmark, and I've been coordinating the Panoramics project. And we have been on a 4.5-year-long journey, and we are now ready to finalize and to conclude on our results and the impacts they may have. We have given our webinar today the title, Unveiling the Invisible, How Effect-Based Approaches Transform Our Understanding of Chemical Mixtures. So who are we? The idea for the project came from a collaboration under the Human Biomonitoring for Europe program, where we were 3 institutions collaborating: DTU and 𝗕𝗄 University in Amsterdam and ONIRIS in France. And we got the idea to focus much more on effect-based approaches for chemical mixture testing. And we invited this consortium, including 𝗕𝗄𝗄𝗏 from Germany, Brunel University in London, University of Southern Denmark, Odense University Hospital, and 𝗕𝗓𝗏, which are all the academic institutions. And then we invited the 3 SMEs, 𝗕𝗀𝗃𝗄𝗄𝗏, 𝗕𝗫𝗃, and TCD Digital, previously called Biomax. In our regulatory scientific advisory board, we have representation from industry, Nestlé, Procter & Gamble, L'Oréal, as well as by the NGO ChemTrust and the European institutions JRC and EFSA, and by USCPA. So in order to set the scene, we have prepared this small video that I'll show to you now.
Every day, from the moment we wake up, we are surrounded by chemicals. When we brush our teeth, when we eat breakfast, or when we head into the world, even the air that we breathe carries a mixture of invisible substances. Alone, each of these chemicals might not seem like a big deal, but together, they form mixtures, and mixtures behave differently. That's where Panoramics comes in. We're a European research project working to understand real-life chemical exposure and how complex mixtures affect our health and the environment. We use powerful tools to detect chemicals in the real world, not just one at a time, but as they actually appear in our lives, combined. Our work helps scientists, regulators, and policymakers make better decisions, so we can all live healthier, safer lives. Because even if we can't see chemical mixtures, they're always there. Panoramics is here to make the invisible visible.
Yes. So what do we mean when we talk about complex chemical mixtures? I'll here show you an example from a European human breast milk sample where we have detected 102 chemicals. Half of them were quantified and half of them were detected by suspect screening at a high confidence level. So we found POPs, persistent organic pollutants, a large number of them, flame retardants, PFAS, blast additives, UV filters, endogenous compounds, pharmaceuticals and personal care product, pesticides, food-related product, and a diverse group of chemicals. So these are what we mean when we talk about a complex chemical mixture. And how have we addressed and investigated those complex chemical mixtures? This is an overview slide of our activities in the project. To the left here is shown our experimental activities. We have taken a NAM and exposome-based approach and have tested samples from the environment, from food, and from humans that represent the European scenarios. And then we have done whole mixture testing and chemical profiling on these real-life mixtures. The aim was to show how chemicals travel from the environment to food to humans, and to compare the hazards between these matrices. In order to identify emerging chemicals of concern, we have applied effect-directed analysis on these samples. Moreover, we have investigated we have made component-based studies of selected chemicals in these real-life mixtures with the aim to investigate if there were any deviations from additivity or not. Then in phase 2 of our project, we have focused on human cord blood, and the aim was there to associate chemical exposures and bioassay activities with reproductive and neuropsychological function in the children. Then we have our theoretical work here, where we have developed a software tool, the chemical mixture calculator. We have performed 4 case studies in order to estimate if there were any human health risks to chemical mixtures. And finally, we have derived effect-based trigger values for water, food, and blood. So this is a slide showing an overview of the bioassay panel that we have used. We selected 22 bioassays that are all linked to adverse outcomes, either to neurotoxicity, thyroid hormone system disruption, reproductive toxicity, or genotoxicity and stress responses. And these assays were selected because they were all robust and sensitive. For phase 2 of the project, where we tested 750 cord blood samples, we selected 6 of the most promising bioassays to test those. And where did we get the human cord blood from? We got it from the Odense child cohort, which is a Danish cohort where children were born around between 2010 and 12, and they have been followed up till the age of 12 years old. And we used exposure data from the mothers from this cohort. We used birth weight data or information on anogenital distance, which is a marker of male reproductive health disorders. But these were the cord blood samples from the Odense child cohort. Then we have performed several different mixture studies for reproductive toxicity and neurodevelopment. And this slide illustrates the various studies we performed. First, we have been doing component-based mixture studies on a few model compounds in a stem cell model. And the aim was to show if there were any additivity or not, and if there were any adverse effects when single chemicals show no measurable effect. And we tested either mixtures of PFAS or pyrethroids or parabens in this stem cell model. Then we have been performing component-based mixture studies based on reconstituted mixtures based on real-life exposures. And we've been mixing around 24 chemicals from 16 environmental, food, and human samples and tested in our bioassay panel. Then we have been doing some theoretical case studies, also based on reconstituted mixtures, with the aim of showing if there are any human health risks to mixtures. And we performed 4 of these case studies. Finally, we have been doing whole mixture studies on extracts of real-life exposures with the aim to see if there were any hazards to these mixtures and to compare the hazards of these samples. And also, we've been doing whole mixture testing on the cord blood samples. So this is the agenda for today. After me, Jean-Philippe Antignac will talk about chemical contamination of our environment and how chemicals propagate to food and back to humans. Then Tome Hamers from Rie University will talk about bioassays for mixture testing. Next, Sebastian Schmeissert from BFR will talk about which chemicals are driving the mixture risk. Then Martin Scholze from Brunel University will talk about what is the chemical mixture calculator and what can it be used for. I will end by talking about impact, successes, and learnings. And finally, there'll be a Q&A session. So please, if you have any questions, you can put them in the chat underway. So, Jean-Philippe, now over to you.
Thanks a lot, Rie, for this setting the scene presentation and introduction. I am very pleased today to give this relatively synthetic and I try simplified presentation regarding the component of panoramics dealing with the exposure measurements from typical samples selected within the project. This what we have done with my institute. So in the next slide, we will address the global strategy we have adopted for documenting this reality of exposure. We have combined two different methodologies. One on the left is really conventional measurement, targeted measurement and quantification of a number of known chemicals for which we have the appropriate method already established. And we have complemented this conventional approach by a global chemical profiling, the so-called suspect screening approach. Here, the objective were to open the window and to permit the detection, at least qualitatively, of a wider number of exposure markers that could be present in the analysis in the sample of interest. In the first case, we get concentration value. In the second case, we get indicator of exposure, such as detection rate or variability in terms of abundance. And we have applied these two approaches to a number of samples from environment, water, from wastewater, effluent, influent, surface water, drinking water, to fish and co-milk, sorry, to human matrices, including human milk and human serum. On the next slide, we have globally what we have done in very short summary. For targeted measurements, we have applied a number of different methods permitting to capture different substance classes and different markers belonging to these different substance classes, from relatively lipophilic contaminant, dioxin, PCB, BFR, organochlorine pesticide, PAH, and also PFAS, phthalates, for a total number of more than 100 exposure marker quantified. And regarding the global profiling approaches, suspect screening, these are presented the global result of the marker detected and identified with a high confidence level. And this number of detected chemicals, depending on the sample type, vary from several dozens to several hundreds. The matrices for which we have detected more chemical was wastewater, unsurprisingly, and also human serum. On the next slide, please. Here is a summary of which substance classes have been detected. So we can try to interpret this as what are the main driver in this real-life exposure pattern we have observed. In brief, the top 5 substance classes detected in those real samples were practically for each sample type the same. Pharmaceutical, personal care product, I mean benzophenone, for example, or parabens, plasticizer, among which bisphenol, of course, pesticide, and some food additive. And the second observation is that, of course, we have detected more than those exogenous chemicals, we have detected a lot of endogenous substances also. In the next slide, I have reported an example of picture illustrating the presence of same chemical across this environment, food to human continuum. I mean the same chemical present in the different sample type. And among this ubiquitous contaminant, outside, we can have, for instance, paracetamol, an example of a very commonly used drugs, of course, DEET also, triclosan, some pesticide, clearly. As I said before, some benzophenone, also personal care products, and bisphenol A or F. All these chemicals are examples of compounds for which we have detected them all across the sample type detected, of course, in addition to other relatively expected compounds such as caffeine, for example. On the next slide, perhaps just one particular focus on an observation that we have written our interest. It was the presence of parabens in relatively high detection rates, especially in human serum. So one information probably to go ahead in terms of risk assessment. And for the last slide, I think, sorry, I have a problem with my own screen. Sorry. Excuse me. Yeah. We have tried to do a little bit more than this qualitative catalog of detected substances, considering that one advantage of suspect screening approaches is not only to detect and possibly identify, but to compare the abundance of those chemicals detected between different subgroups of sample. And this will be better explained later with the Tome Hamers presentation, but I just introduce here the global approach. What we have done is to select two different groups of human sample, human serum. One corresponding to serum sample for which a given relatively high level of biological activity have been determined by bioassay, or human sample for which the corresponding individual presents a high level of a particular health outcome. And the second group of sample was a serum sample associated to a low biological activity and or low level of health issue or health problem. And we have chemically profiled all these different samples and operated the differential approaches consisting to compare for each detected signal the abundance observed between the two groups. And of course, the purpose was to point out chemical possibly associated to a high level of bioassay or health concern. But again, this will be better explained later on in the next presentation. So I come directly to my conclusion very briefly on the next slide. Panoramics lesson learned for the scientific community is probably that the work consisting to couple chemical profiling and bioassay is certainly promising and very interesting, but still face some technical issue, I think, in terms of alignment to be relatively sure to work exactly on the same sample extract and to rely correctly one given signal in bioassay, possibly reliable to one particular chemical. It's very, again, some technical issue among there, so work for the scientific community. And globally, the second lesson learned is certainly that the combination of targeted and both non-targeted is now relatively common and probably the future of exposure assessment in combination with hazard characterization. For public health authority regulator, I would say that this global chemical profiling approach certainly contributes to improve our knowledge about the reality of human co-exposure by this qualitative information. This new type of data may be certainly used for prioritization based on what we observe in reality, and also for early warning purposes. And this approach should be included in monitoring program. From now, I think they are sufficiently mature as a complement to conventional targeted approaches that will not be replaced. This is important. And for citizens, this kind of global profiling approach, of course, open our vision about the reality of co-exposure. So by definition, they improve the protection of individual and ecosystem through this improvement of our knowledge about the chemical in our environment and food and biological living organism. So this is the end of my talk, and thanks for your attention.
Thank you, Jean-Philippe. Now I'll give the word to Tome Hamers.
Thank you. Thank you, Rie. Welcome to this presentation. My name is Tome Hamers. I'm from the Vrije Universiteit, and I was selected or appointed or give this presentation, but I should say that this is really a group effort. I'm going to present results from 5 work packages that all have some link with bioassays and biomonitoring, and we try to integrate that into a single presentation. Well, the idea of the whole presentation is that we consider the chemical mixture as to have an analogy with an iceberg. They both have a risk. But usually what we know is what we see, and that's the tip of the iceberg. And these are the chemicals that we are aware that are in our samples, that we can quantify also, that we know the toxicity of, that we maybe also monitor regularly, and if we know their identity and their concentrations, we can do mixture modeling and calculate the potency of these mixtures. And also because we know their identity, these chemicals can be regulated. And the big unknown part is what's underwater, and that contains the unknown chemicals, of course, the chemicals below detection limit, transformation products that we are not aware of. And so the mixture effect of these is difficult to assess, and also regulation cannot be done on what we do not know, basically. So the whole idea of this presentation is that we used effect-based monitoring with the idea that this could capture the mixture toxicity of the whole iceberg, and then could tell us more about the total toxicity of the whole mixture. Well, what we did in the first instance is that we collected samples from all over Europe, and we pooled them all together to get a real typical sample from Europe. And these were different matrices that we collected. We call it the environment, food, human continuum. We collected samples from water, from fish, from milk, human breast milk, as you can see, and human serum samples. Water, we took several types of water: wastewater, effluent, surface water, drinking water, bottled water. We bought from supermarkets. We collected aquacultured fish and wild fish collected from the oceans, fat fish, lean fish. We collected cow milk, and there's a distinction between organic cow milk and conventional cow milk. A human breast milk sample was included, and we had several serum samples, mainly from adults, from Denmark, from Australia, also to compare to other continents, from Europe, a mixture, a female bearing age, so female samples from women in the bearing age from Australia, and we got cord blood samples from Denmark. We tested all these, we made extracts of these samples, and we tested them in bioassays that represented several AOP networks, or at least the molecular initiating event. So we selected AOP, we had a focus within panoramics, I should say, on thyroid hormone system disruption, on developmental neurotoxicity, on reproductive toxicity, and on genotoxicity. And we selected bioassays that represented molecular initiating events, at least, and some of them also had represented some key events further in the AOP. And as Rie already pointed out, altogether we had 22 in vitro bioassays, and I'm not going into detail now about exactly the bioassays, but I just want to give you an overview of what came out. Okay, so here's the, do I have a pointer? Yes, I get a pointer. No, I don't get a pointer. Okay, that's fine. You can see my mouse, hopefully. No, you cannot. We have samples from water, fish, milk, and blood. You can see them here: wastewater, effluent, surface water, drinking water, bottled water, etc. And as Jean-Philippe nicely pointed out, we did a suspect screening, and we could see already that the chemicals are ubiquitous in the continuum from water, as you can see here, to humans. That's the order they are presented as well. Next. Page down. Nothing happens. I'm stuck. Yes. So altogether we had 547 chemical features identified. In Philippe already pointed out how they were distributed among the different samples, and 63 of them were ultimately identified, and 24 of these were also quantified by semi-quantified, I should say, with sufficient confidence about the concentrations. And these are the 24 chemicals that we also took later to reconstitute a mixture of. And you can see them here to the right in this picture. And you can see from wastewater to the left to effluent, surface water, drinking water. Of course, wastewater had the highest responses in our different at the highest levels of these chemicals. And then to the right, you can see how it propagates into human samples. And our conclusion from this was that many chemicals, not all, as Jean-Philippe also pointed out, are ubiquitous and also are present in the full environment, food, human continuum. And this is the famous list of 24 that we ultimately worked with. So these chemicals we also reconstituted mixes with to be tested in our bioassays. Now, before we did that, we also tested, of course, these extracts. So here you see exactly the same information as on my previous slide. And here are the results from the bioassays. You can see them being categorized per AOP network. You see the different bioassays here. And you can also see again from if you go through the continuum from drinking water to wastewater to fish, milk, human blood, you can see basically an increase in all the different bioassay responses. What you see on the y-axis in this graph is the relative enrichment factor we require to obtain a 10% effect level, and it's an inverse axis. So that means the higher you get, the more bioactivity we measure in these samples. So what we ask ourselves first is, if we now just take a look at the tip of the iceberg, we know what's in there, so we can then also calculate the bioactivity that we expect from this. So if we know the relative potency of these chemicals in our assays, the rep here, and we know the concentration that is quantified, we can calculate the activity in terms of a bioequivalent concentration. That means the concentration of a reference compound that would give the same response as the complex mixture gives to us. And we call that the Beck-Gam, the bioequivalent concentration based on the chemistry that we know. And what we then did is we also reconstituted this mixture, reflecting the ratios that were analyzed in water, in fish, in milk, in human breast milk, and in blood. And we tested them in our bioassays. And luckily, I would say, we found a nice one-to-one correlation between the two. So this means that the chemicals that we are aware of that are present in the tip of the iceberg, if we put them together in a bioassay, what we measure is also what we predict by using concentration addition. So that was what we expected, but we were also happy to find it. Now this is the tip of the iceberg, but of course we are interested in the whole iceberg, and we can then also determine the activity in our 22 bioassays for the whole iceberg as such, for the extract that we made from the whole iceberg. And what we usually see here is that we find a higher activity, a bioequivalent concentration based on the bioassay, then we can compare with the chemistry, because the total iceberg is bigger than just the tip of the iceberg. So there is a part that we cannot explain. That was the expectation that we also had on beforehand. And that's also what you see here. What you see here on the x-axis is the predicted activity based on the chemistry that we know. And what you see on the y-axis is what we actually measure in the bioassays. And you can see that in practice, that is in many cases more than 100 times even higher than what we expect on what we know is present in the tip of the iceberg. So we had a big interest to find out which chemicals are these that are unknown and that contribute to this bioequivalent concentration, to this activity that we measure in the assays. And we should realize that these are not only xenobiotic compounds. Of course, we are interested in xenobiotic compounds, but this also contains quite a lot of endogenous compounds. That these can be fatty acids, these can be proteins also that give a response in our assays. We did do some work to avoid having hormones, endocrine disrupting assays by preparative fractionation, for instance. We removed hormones, but in many cases we still had other endogenous compounds present in these extracts. Now, what we did, we took a effect-directed analysis approach, and this is how it goes. What you see to the left is the extract that we have, and we inject that on the 𝗕 an 𝗕 apparatus, and then we do a detection on a QTOF, and we get, of course, a chromatogram. So that's the chemical output that we get from our extract. And on the other hand, we fractionated our extract. We did a second injection. We fractionated our extract, and then we collected what came out of the 𝗕 in a 96 well plate, as you can see here. And the 96 well plate, we then tested in our bioassay, and then we got what you see to the right bottom. That's our biological chromatogram, our bioassay chromatogram. And we then align them and try to identify which peaks that we measure in the chemical biogram corresponds to the peaks that we see in the bioassay chromatogram. And here you see results of such a bioassay chromatogram. This is an example from the TTR binding assay. And what you see here are the 5 different samples, the serum samples that we tested. They are normalized against the procedural blank. And you can see the different samples give also different peaks. The one to the left is from the S5, from the European sample. The one in the middle is from the Danish sample, that's S1. And the one to the right is from the cord blood sample from Denmark. So we can really see different profiles in these fractionated samples. And we can then come up with different candidates of compounds that we think could explain these bioactivities that we have measured. And here you see some candidate compounds. You can see here the identification level in the middle. That means L1 means that they are really confirmed. This compound is present in that fraction, while L2 and L3 are probably present or have been suggested to be present. So they have a lower confidence level. And you can see then that this is the whole idea of effect-directed analysis, that we come up with candidate compounds and that we can then indeed identify them and also test their activity in the bioassays to confirm that. We also did an exercise on the 750 cord blood samples we got from the Odense child cohort. So this is the working flow that we took there. We had cord blood samples from 750 newborns. They were extracted and we tested these 750 extracts all in 5 different bioassays. And we also did some some chemical identification of these samples, and we tried to do effect-directed analysis on that as well. We also tried to make a link between what we actually measured in the bioassays and what we analyzed in these 750 cord blood samples, a link to health outcomes, and we had a specific interest, as Rie already pointed out, on IQ, on ADHD scores, on vocabulary scores, and on anogenital distance. Now, here are the results from these selected bioassays, 5 in total. And again, the higher they are plotted here, the more bioactivity was measured in these samples. And you can see here nice distributions. And you can also see that they are kind of log normally distributed, also as we would expect they were. And what we did then is pool samples that were in the higher end, samples with high bioactivity. We made pooled samples from, and we also collected samples from the lower end with the low bioactivity, and we made pooled samples out of that. And then here again, you see such a nice bioassay chromatogram. You see the activity again on the y-axis, and you see the fraction time on the x-axis. And what you can see here, what means Boy's high effect and Boy's low effect. These are the pooled samples with a high, in this case, activity in the TTR binding assay, girls with a high activity in the assay, and low means that they had a low activity there. And you can see really that there are typical peaks in this chromatogram that go together with the boys that had a high effect and the girls that had a high effect. And out of this, we came again up with candidate compounds. And here, this is only based on the single TTR binding assay, but we did this for all assays that we did. Chemicals that have been identified at least at level 2 and level 3 of identification that belong to different groups. Similarly, as Jean-Philippe already pointed out, pharmaceuticals, you can see here, nutritional supplements, a lot of endogenous compounds, as you can see, and also other applications. Great. So that was one way to do it, effect-directed analysis. The other way to do that is to do this differential analysis that Jean-Philippe pointed out. So to look at the peaks that are found in samples that have a high activity and also samples that are associated with a poor health outcome. That's the red chromatogram. And then subtract from that the other sample, the other pooled sample that was associated with low bioactivity or with a good health outcome, and see which peaks dominate this mixture. So here you see the outcome of such an exercise. So what you see here on the, I will take some time to explain this graph. What you see here on the x-axis are the different health outcomes: ADHD scores, AGD, the anogenital distance, IQ scores, vocabulary scores, and the plus and the minus indicates what is actually a poor situation. So an increase in ADHD means that that is a poor health situation. But for the other endpoints, AGD, IQ, and vocabulary, a decrease would mean that there is a poor health condition. And to the right, you see the AR, the IREC, the MMP, the NOI, the TTR. These are the bioassays that we tested. And in general, of course, the higher the bioactivity is, the less undesirable this situation is, the less unfavorable the situation is. Now, what we put on the x-axis is how chemicals dominate the poor situation. So the poor health situation, these are above the line 1. and the high bioactivity is also given here. And we just picked here two compounds that had clearly a profile that dominated the poor health situation. That's chlorophenoxylatic acid, for instance, and propylparaben. Propylparaben is present in cosmetics, as Jean-Philippe also showed you, and chlorophenoxylatic acid is a pesticide, a herbicide that's also used as a growth stimulator in agriculture. Of course, we also see some they are also negatively associated, let me put it that way, with the health outcome. But we were, of course, more interested in what is above the line 1 here than below. And this gray area indicates a twofold increase in peak intensity of these chemicals. So these are chemicals that are definitely on the short list to have a closer look at. Okay, so far for the identification of the bioactivity. The final part of our presentation will be about how we should interpret the bioactivity that we measure in our samples. And basically, we want to bin them into two groups. If we have several samples and they all give an activity in a bioassay, giving an activity as such is not really a hazard per se. So we have to bin them in some way into acceptable bioactivities and in non-acceptable bioactivities. And for that purpose, we have worked quite a lot on developing effect-based trigger values. So that means that we could say, okay, samples that have a bioequivalent concentration or bioactivity above a certain value, they go into the non-acceptable bin, and samples that are below, they go into the acceptable bin. And we need to find a way of deriving these different effect-based trigger values, or the EBTs, as we call them. First of all, I want to go into, so I'll present this per matrix. I'll start with the water, then we do the fish milk, and then we do the human samples. Now for water, EBTs have been derived previously, work by Neil and by Beate Escher, on deriving EBTs for drinking water and EBT surface water. This has been published, and we basically took a very simple approach here, assuming a 10% dilution in surface water. We got an EBT for effluent, which is 10 times higher than the EBT for surface water. And we took another assumption that there's 90% removal of a compound in the wastewater treatment plant. So the EBT based on wastewater is 10 times higher than the EBT in effluent. So if we adopt these EBT values, we can then compare what we have actually measured in our water samples compared to these EBT samples. And that's what you see here in these graphs. So here you see a graph for wastewater, for effluent, for surface water, for drinking water, and for bottled water. And on the x-axis, you see the effect-based trigger value that we have derived based on the assumptions made above. And on the y-axis, you see the actual activity that we have mentioned. So that means you see also the 1-to-1 line. So that means every assay that is above the 1-to-1 line basically exceeds the EBT value. And as you can see here very nicely, we were quite doing well here with these estimates, particularly the estrogenicity is the kind of effect that exceeds these EBT values. And that is also very much in line with the current adoptions in the Water Framework Directive, where there will also be room to use bioassays for monitoring surface water in the future. So for food, no effect-based trigger values did exist so far. So what we did here, we took health-based guidance values, HBGVs, as a starting point, and we derived, or we didn't derive them, we looked up HBGVs, so like acceptable daily intakes or tolerable daily intakes, or DNAL values for the 24 chemicals that I've shown you previously that were found in the whole continuum. So we made an assumption there. We gave an allocation factor to the food items. So that means how much of the HBGV could be present in the consumption of fish and milk. We set it at 20%. We have the HBGV value, we have the body weight, and then the consumption per kilogram of body weight. In that way, we can then calculate which food concentration, which concentration in fish or concentration in milk corresponds to the 𝗕𝗵𝗲𝗃. We can then calculate that in a bioassay activity by multiplying it with its relative potency. And then we have, for all these 24 chemicals, we have calculated what the 𝗕𝗵𝗲𝗃 should be in terms of Beck. And what we then did, we defined the EBT is the median of these Beck values, which were very nicely log normally distributed. And here you see the results of that exercise. So here again, you see on the x-axis is plot the EBT value that we derived, and on the y-axis you see what we actually measured in our samples. And here you can clearly see, because everything is above the diagonal 1-to-1 line, that that for all these bioassays, the activity that we measured exceeded the EBT that we derived in this particular way. And that also confirms basically what we already knew from the previous exercise that I showed, that just the tip of the iceberg cannot explain the full bioactivity that we measure. It also makes sense because the EBT here is derived from health-based guidance values, so which are actually derived for single chemicals, so they do not take into account this mixture effect. We also in this slide I only show you the what we measured, the Beck bio. We also calculated the bioactivity based on on these 24 chemicals that were present, and in that case they were all below the EBT. So that means indeed if we only use the tip of the iceberg, we find indeed that they are all below the EBT that we derive on this compound by compound based EBT. For human blood, we took quite a similar approach. Actually, we took 3 different approaches, and I'm going to show you the 3 different approaches that we took. So again, we took here the 𝗕𝗵𝗲𝗃s from all annotated chemicals that we had that were detected in human blood. These were over 200, but unfortunately we could only find 32 health-based guidance values, so acceptable daily intakes, tolerable daily intakes, etc. We then derived the corresponding plasma concentration using a toxicokinetic model, and we calculated this plasma concentration into a bioactivity concentration again by multiplying with its relative potency that we determined in our bioassays. And again, we took here the EBT that was based on 𝗕𝗵𝗲𝗃s. We defined as the median of all these different 𝗕𝗵𝗲𝗃s that were calculated into Beck concentrations. And by doing this, I'm not going to show it, but all human cord blood samples exceeded the bioactivity that we measured by this particular EBT 𝗕𝗵𝗲𝗃. They actually exceeded it by quite a big factor, by more than a factor of 100. We also did then the same with the calculated, so with the tip of the iceberg that you see here on the y-axis. So this is only what we know is present in these samples, in these human serum samples. And if we do that, then you see nicely that they all obey to this EBT value. So it seems that if we work with EBTs that are derived from health-based guidance values, that it covers really nicely the tip of the iceberg, but not the whole iceberg. Then we took another approach because we had all these samples, 750 cord blood samples that we had analyzed. So then we said, let's now consider the 95th percentile of all these measured activities as the EBT. So we call it the EBT P95, based on the 95th percentile. And here you see how we did that. So here again, you see the result in these different bioassays. And then we said just, okay, let's take the cutoff point of 5%. So in all these cases, by definition, the EBT is now set at 5% of the actually measured concentrations. And then we compare that to what we found in other studies. We had one study in-house where we previously had determined the same TTR activity as you see in the left panel in cord blood samples from a different cohort. And you can see that there's, unfortunately, these were only 6 samples, but you can see that these 6 samples are indeed below the EBT that we derived. The EBT is around 10. And you can see here that the highest is around 2.5. So it seems that we are in the right range. We would not expect, based on only 6 samples, that we would have samples that exceed the EBT. We also had data for another bioassay, that's the neurite outgrowth inhibition, the NOI assay. Yes. Here you see the results. These are results from a different study. This is a German cohort study where you can see that about 27% of the samples here exceeded the EBT that we derived based on our cord blood samples. And there can be many reasons why that is the case. We use serum, they use plasma, we use cord blood, they had pregnant women. Blood, they use different extraction methods, but it seems that this 5th percentile is indeed in the order of magnitude that you would require to get to derive an EBT value. The last approach that we took is the associations that we studied between the bioassay responses and the health outcomes. So we derived an EBT associated, ASOC we called it, derived from the association between health outcomes and bioactivity. I'm not going into detail about the whole association study that we did in the sake of time, but I'm going to jump directly to the results from that. We did not find that many associations. What you see here is the regression parameter on the log scale here for the different associations. And what you see here, we tested the association between TTR and the anti-androgenicity, NOI, oxidative stress, and mitochondrial membrane potential for the different health outcomes that we had: IQ, ADHD, vocabulary, and language complexity, and anogenital distance. And if you see a green dot, that means this the median is located in the area where that points to a good health situation, while if you see a red dot, that points to the area where you have a poor health situation. As you can see, many of these confidence intervals include 0. So that's the log of 1. That means that the regression coefficient, that there basically is no relationship between the bioassay response and the health outcome. There may be several reasons for this, why this is the case. The adverse outcome is, of course, a very complex one, and there's not a one-to-one relationship to the MIE. Biotransformation is hardly covered in our bioassays, etc. So there may be different reasons why this is the case, but we found one significant correlation here between neurite outgrowth inhibition that we tested in vitro and IQ scores. So this neurite outgrowth inhibition was tested in extracts from cord blood and had an association with the IQ scores of these children at a later age. And based on that association, we also derived a value for this EBT, effect-based trigger values. So we had this association between NOI and IQ, and this EBT is based on a 1-point decrease in median IQ score for the test population. And if we use that EBT value for our own cohort, we see that 11% of our samples exceeds that EBT. So again, we are quite well in the range where we expect the EBT to be. And if we use the same EBT based on the other study that I've shown you, the German study, you see again that there's bigger exceedance here, similarly as we've seen with the previous EBT that we derived. Okay, this brings me to my concluding slides, lessons that we learned regarding bioactivity and contributing chemicals. First of all, the mixture effects in bioassays seem to be well predicted by concentration addition. That's what we expected also, but it was very nice to confirm this with the experimental work that we did. Quantified chemicals only explain a small part of the observed bioactivity. There is a background response due to non-quantified or unknown chemicals, which are partly endogenous, and we don't know exactly how big this contribution is. We explored different strategies to identify unknown bioactive chemicals. I think we were quite successful in applying EDA to new matrices. This has never been done in blood, for instance, including human matrices. And also the differential analysis of chemicals with the peaks that were present in the chromatogram from the non-target screening in the samples with poor health compared to good health, gave us indication of chemicals that could explain the measured bioactivity. Regarding the effect-based trigger values, we can conclude that we have made a first attempt to derive them from not only for water but also for fish, for milk, and for human samples. The EBTs for water distinguish the samples with acceptable and non-acceptable bioactivity quite well. For the first time, we derived EBTs for fish, milk, and human samples. It seems that EBTs that were derived from health-based guidance values are too conservative for measured activity in bioassays, for the 𝗕𝗀𝗏𝗃𝗏, but not for calculated bioactivity based on the chemicals that we know are present in the tip of the iceberg. And the EBTs for human samples were derived in cohort studies. We based it on the 95th percentile of measured bioactivities or on the observed association. And we seem to be in the right range if we take that approach. And of course, these numbers are not written in stone yet, but we made a first attempt to derive these values. And I think we need more proof also from other studies to further corroborate these EBT values. That was my presentation. Thank you for your attention.
Thank you, Timo. Now I'll give the floor to Sebastian Schmeissert from Univ.
Yeah, also welcome from my side. My name is Sebastian Schmeissert. I'm a regulatory toxicologist at the German Federal Institute for Risk Assessment, BFR in Berlin. And it's my pleasure to also summarize 2 work packages. And in my presentation, I want to give you an overview of the chemicals we have identified in panoramics as the main contributors to calculated mixture risks. So to shed more light on priority substances, we looked at human co-exposure with a different set of data. In particular, we used component-based approaches to scale the contribution of each chemical component to potential health effects related to reproductive health and neurodevelopment. And we also performed epidemiological analyses to investigate whether there is a potential association between chemical mixtures and health effects such as reduced birth weight or ADHD. So what is a component-based approach and how can we use it? The approach is commonly applied in mixture risk assessment when the mixture composition is known. The mixture risk is estimated based on the contribution of each individual component and the default assumption of how mixture components may act jointly is dose addition. Appropriate hazard and exposure data for each component is required. In panoramics, we focused on pre- and postnatal co-exposure in a series of case studies, and here we assessed complex co-exposure detected in panoramics, in particular in umbilical cord blood and human breast milk for potential mixture effects on the developing reproductive, nervous, and immune system. To provide some background, the following outlines the basic steps of a component-based mixture risk assessment. you start with the problem formulation, which addresses two key questions. So first, what is the mixture to be assessed? So what chemicals are in the mixture? And then the second, what is the exposure scenario? So target population and exposure conditions. Then you would go on to collect relevant hazard and exposure data for each individual component. Hazard data may be provided by in vitro or in vivo studies. Exposure information may come from modeled or measured data. So it's essential here that both your hazard and exposure data is relevant to your exposure scenario. From here onwards, each chemical component is assessed as if it were a single substance. Within hazard assessment, effect data would be evaluated to derive toxicological reference value. And within exposure assessment, quantitative exposure levels would be assigned to each substance. Thereafter, you would calculate for each mixture component a hazard quotient, which is the ratio of exposure level to toxicological reference value. And in order to estimate the total risk of the mixture, you would then sum up all these hazard quotients to obtain a hazard index, which is then a measure of risk, and a hazard index above 1 is indicative of a potential risk. It's important to note here that the hazard index provides only a rough measure of likely toxicity, and its numerical value should not be interpreted as a direct estimate of risk. The results of a component-based approach are usually depicted in the form of a so-called waterfall graph. Here you can easily spot the risk drivers, so those substances that contribute the most to the mixture risk, and in most cases only a few substances dominate the entire risk, and many others do only insignificantly contribute. So in panoramics, we integrated different types of data. On the exposure side, we always started with the chemicals identified with our analytical workflow, and the exposure levels were either measured directly in the samples or predicted through modeling. On the hazard side, we use both in vivo and in vitro effect data. And in order to use in vitro PODs, you had to convert the daily intake levels to internal exposure levels using toxicokinetic simulation. So here are some of the results we obtained in the case studies. The three waterfall graphs show the contribution of single substances or groups of substances to the health outcome. As you can see, all the hazard indices are clearly above 1, indicating potential risk. The corresponding risk drivers are indicated in the table below, which are dioxins and dioxin-like components, and bisphenol A for reproductive toxicity effects, non-dioxin like PCBs and bisphenol A for neurotoxicity effects, non-dioxin like PCBs, PFAS, and bisphenol A for immunotoxicity effects. So summing the results we obtained in our case study, the main risk drivers turned out to be legacy persistent organic pollutants, POPs, and bisphenol A. The POPs are listed here: dioxins, dioxin-like compounds, polychlorinated biphenyls, legacy pesticides, brominated flame retardants, and legacy PFAS, and they are already strictly controlled, banned, or severely restricted. And also for bisphenol A, there are already restrictions in place. Epidemiological analyses are another way to look at mixture risks. Here we use data from the OTAN's child cohort, which is an ongoing prospective Danish birth cohort. and to investigate whether there is a relationship between prenatal exposure to endocrine disrupting chemicals measured in marginal blood and urine and various health outcomes such as birth weight or neurodevelopmental outcomes. We used statistical analysis to evaluate potential mixture effects via 𝗕𝗀𝗃𝗃𝗃𝗃 computation. I hope I said that right. Which is a statistical method that analyzes changes in health outcomes associated with a quartile increase in exposure and relative contribution of each chemical in the association. A summary of these studies is shown on this slide. So overall, moderate, non-significant associations between higher EDC exposure and adverse health outcomes were observed. However, for two groups of chemicals, we found statistically significant effects. For a group of phthalates, we found statistically significant positive association with ADHD scores. And for a group of PFAS, we observed a statistical negative association with birth weight and vocabulary percentiles. So as for each mixture risk method, their strengths and limitations. And here they are exemplified for the component-based approach. Strengths are that it's a pragmatic approach to estimate mixture risk. It's data-driven and useful to identify risks, risk drivers and critical health effects. And it's relatively easy to apply based on available single substance data, so no testing is required. Limitations are the limited scope, time and resource constraints, data and knowledge gaps, uncertainties arising from the hazard and exposure assessment of each component, and those from the mixture assessment, for example, with regard to the grouping. And often the data you use are very heterogeneous in terms of their relevance to the exposure scenario and the data quality. So these limitations raise the question whether a component-based mixture risk assessment approach is really suitable for assessing complex mixtures. And alternatively, whole mixture testing strategies, as those developed within Panoramics, we think hold great potential to address complex mixtures. So what did we learn in the process? First of all, assessing the risk associated with coincidental co-exposure is and remains challenging. Only a small number of individual chemicals or groups of chemicals contribute substantially to potential risks. Exposure levels often exceed the visual effect thresholds, so the HQ would already be above 1, suggesting that regulating single substances already would reduce the mixture risk substantially. Major risk drivers are legacy chemicals that are already restricted or banned. Risk mitigation measures are already in place for some of the substances like BPA and phthalates, but they may be inadequate to substantially reduce the exposures. And most importantly, additional efforts are needed to reduce exposure to legacy POPs. And this is it from my side. Thank you.
Thank you for your presentation, Sebastian. Now I'll give the word to Martin Scholze from Brunel University.
So all I have to do is press it. Okay, I'm Martin Scholze from Brunel University in London, and I have the pleasure to introduce you in one of the software tools we developed in the project. It's so-called Chemical Mixture Regulator 2.0. So, what was the motivation and the objective to do this? What you just heard in the previous presentation was a focus on compound-based approaches, mixture modeling approaches, meaning you're coming from single compounds and trying to build up to understand the combination of them. And that's also behind the rationale behind the calculator. So we wanted to develop a software solution to estimate the potential impact of chemical mixtures on human health the best possible way. And as you heard, trying to find out what chemical the drivers of the combination effect, so the mixture drivers. And we wanted to have this for as many compounds as possible and not restricted to certain classes. This was the main motivation for the chemical mixture calculator. Before I go into more details and more background, what you can do and not, just the team behind, mainly responsible for the technical implementation of web design and everything, was TGG Digital and Biomax. I was involved in the data pipelines, the DTU team for the AOP alignments, and Sebastian was, as end user, mainly responsible to provide always critical feedback, which we had to follow strictly. So what is really the magnetic mixture calculator 2.0? First of all, the name already indicates there's a first version out, which the DTU developed a couple of years ago. It was based on human health-based guidance value and or PDOs, a point of departures from animal data, and also on real exposure measurement, with the consequence it was limited to a quite small number of compounds for any kind of mixture calculations. We wanted change. We wanted to expand the spirit of the Panorama project to a large number of substances, and also a little bit bring in the AOP or the NAM idea. So we restricted us on hazard data only derived from in vitro assays. Unfortunately, it became very clear we could not use real measured exposure measurements, so we had to find ways to predict this. And we focused restricted also only on reproductive toxicity and development toxicity. Most important here is a web link. It's a web-based tool and public available, so I encourage everybody outside, go there and use it. Also, future is, having said that we are not restricting to a certain number of pounds, it's batch processing involved. So in principle, you can here investigate mixtures of a few thousand substances. So what is the concept? I mean, we have just heard nice introduction in the competence-based approach, where we have to consider all a single substance, what toxicity value, what effect level we are using for single compounds, and what exposure value. On the right side, you see how we utilize the hazard stream. So we started with all high-throughput in vitro assays available in the public domain, and I will come back later how. This was aligned to AOP knowledge and filtered to these two types of toxicity. And the aim was really to come out with a benchmark concentration value, BMC. It's a potency value directed to an effect level most close to the controls, which still allows reliable, stable BMC estimation, potency estimation. So each in vitro endpoint has its own effect level. So that's why we are not using EC10, EC20, EC50, because very often they don't make sense. On the left side, exposure, we had more problems. So we came very clear to realize that we had to find a way to predict daily intake value. And then, as already mentioned, convert this via PPK modeling simulation into steady state internal blood concentrations. And then once you have this data, you can make the hazard quotient calculation, and then the sum of them is a hazard index. That's the easy part. So, coming a little bit more details regarding the exposure. Here we utilized the exposure forecasting tools provided by US EPA, also better known ExpoCast, which is a multimedia, multi-pathway framework with the aim to predict median intakes for population or for demographic subgroups of the population. Was first big model framework called SEMN2, was published, I think, or released 15 years ago, which covered 8,000 substances and for general population and subgroups, like male, female children, which we utilized. And then for a larger group of substance was expanded under the umbrella of the SEMN3 modeling framework, and this was only for the general population. So that's what we used as intake values for each compound. And we also not only use the median intake values, ExpoCast also quantified the uncertainty in the best possible way. So on the right side, then see the conversion path, how we converted the intake value in internal human plasma. We are the so-called HTTP platforms, also developed by US EPA. It's a generic model structure form, so it's a low-tier approach and includes the most relevant, I would say, compartments. The beauty is you can simulate over 8,000 substances. And also implemented is a probabilistic approach, meaning for the same intake, you can simulate distribution, which includes or covers not only statistic variability, which is hidden in the whole HTTP platform, but also the variability coming from the human probability. And output was then again to match the intake values for general population and different population. We got always a median value and a higher value as a percentile from the Monte Carlo simulation. Hazard, here we used from the Comtox, probably most of you know, familiar, the in vitro DB database, which have nearly 8 million entry, with each entry summarizing one experimental outcome. This was filtered down to only the positive hits to the experiments which we revealed in the confidence PMC estimate, which we ended with nearly with around 280,000 entries. Again, curated via the ICA platform, which we brought it down to 250. And then we used our own filter, which means focus on reprotox and development DNT and aligned to AOP knowledge. So our tool has around 70,000 entries, which means that at least one entry, we have for 8,000 substance, at least one entry. We are covering around 512 assay endpoints, and they are aligned to 125 MIEs or key events. Coming to the web portal interface, how is it working? Again, I start here with a link. First time you have to register yourself, meaning you have to provide your name, username, and your email. It's always a two-factor authentication process, meaning you can work on the tool and store your progress and come back and go on. We have provided a webinar on Monday. It's also available on the Panoramics webpage. So if you want to have more details, how it works, backgrounds, etc., please go there. Roughly how it works, operates is first of all, if you're using this, obviously you have to define your mixture scenario in terms of the chemicals, exposure, hazard values, and the population you're focusing on. Then it includes many refinement filter search tools, which helps you to get rid of this huge chunk of data you might face. And with the aim at the end, you will select to find a final in vitro potency estimate. and then it goes on the hazard index calculation. Just to emphasize, I will show you some screens from the tools, just as an appetizer. Here you see it's the main website for your operation, where you have to make some different decision. I will not explain the details. Please go to the webinar or just use the tool and you will find out. For example, there are different windows opening. Here's exposure, some explanation we provide. We have different visual tools implemented, which helps you to group, to refine, to search. And at the end, the outcomes hazard index for different scenarios, depending on the confidence settings. And also, which is very important, which we find out very important, it includes also an export function where you can export the main outcomes. For example, if you want to replace the exposure estimation with real measurements, you can do it very easily outside this tool and make your own hazard index calculations. So what are the pros and cons? Well, first of all, it's a pragmatic screening. That was the main aim. So it's not a tool to do mixture risk assessment. It's a first step before you're planning to do a proper mixture risk assessment to find out where might be the real problems, to allocate better your resources. Then also strength is having in mind where we aiming in the risk assessment. It's a NEM-based approach. So it's mainly only based on in vitro activity values, in silico, and AOP knowledge. It provides more structured tool for all the in vitro data evidence might face for your compounds. And most important is open access is free to use. And as I mentioned, the export function, so you can build around then your own problem, use it to solve your own problems. Limitations, of course, we don't know exactly what to expect in the future if you're saying NEM-driven mixture risk assessment. So that's why I label it here as a pragmatic screening tool. We have tried also to implement in the best possible way AOP knowledge, but as you know, if you're working in the field, AOP field is evolving daily. We see new knowledge arriving, especially focus on networks, very important. Also, what I realized is in vitro world mirrors a little bit the in vivo world in terms of we have data-rich substances which have been tested on many different assays, and then we have compounds where we have only 1-2 entries. Also, keep in mind, negatives are not included, so we have only positives, because it's not so easy to define a reliable negative. The focus was always on positives. And then we have uncertainties, especially coming from the exposure side. We are using intake exposure values from the US, for the US population, US. So keep this in mind. So how to use it for what? What could be the scenarios you might use? You might really find it very useful. Generally, the tool you can come from two different directions. Either you have a mixture, a composites, you have list of substance, and you want to know a classical in vitro profiling. You can use it. What is out? What is the evidence for the compounds? And it already directs you in the potential problems if it comes to toxicity endpoints upstream. Or you can come up from a hazard side, from an endpoint, and figuring out where's the evidence, which groups of chemicals might be affected or not. Another front, and that's how I like also here to mention an extra slide, is one cornerstone is the mixture risk assessment human side. It's the so-called cumulative assessment groups. On the right side, you see here something from the EFSA guidance documents, guidance how to find out the best grouping criteria. the criteria. In the future, we are using AOPs more and more. And here I see really the advantage also of the tool, because they provide us a mechanistic basis, a better basis to answer two key questions we are very often facing. And finally, the 𝗘𝗃𝗃 is how to translate similarity into a 𝗘𝗃, and also how much is adversity really supported by AOP network knowledge. So that's where this tool might also help you a little bit to guide you into these decisions. So take-home message. First of all, as mentioned, it's a user-friendly tool. It's for the first step of the mixture risk assessment, and it includes some flexibility. It gives you some flexibility. But keep in mind, it's just to support an MRA. The aim is not to replace it. Also, it doesn't provide a push button solution. You're pressing one, you're plugging in some data, press one button, and then you get something. You can do it, but it's not what we suggest. So you need always a little bit of knowledge about the mixture risk assessment field. And again, I provide you here with a link, public available. We have webinar already produced, and we will also come soon out with guidance material manuals and so on the publication, obviously. I think that's all what I want to say. Yes. Thanks.
Thank you, Martin. Now we have come to the final presentation, where I'll talk about impact, successes, and learnings from our project, and sum up what has been said in the previous presentations. So, first of all, one of our findings is that environmental chemicals, as they occur in real-life mixtures, do not interact in crazy ways. They act according to the concentration addition principle, usually. And we found evidence for that in all of our experiments. However, the additivity of chemicals also means that even low levels of a larger number of chemicals has the potential to exert a marked adverse effect. But additivity also brings good news for risk assessors, as it means that mixture effects can be predicted on the basis of single chemical data. So we have shown that whole mixture testing in bioassays is powerful for evaluation of adverse effects of complex chemical mixtures. You have seen another version of this figure before by Timo. We see the adverse effects on reproductive toxicity and neurodevelopment increases when you go from drinking water to surface water, effluent wastewater, up to foods, milk and fish, and to human blood and breast milk. And this is a powerful effect-based approach to reveal the invisible complex chemical mixtures that are present in these matrices. So what are the implications of our result? Synthetic organic chemicals, including industrial substances, computer product ingredients, biocides, and pesticides, disperse through water systems and the environment and accumulate within living organisms, including humans. Most mixture effects are caused by unknown or unmonitored chemicals, posing a significant gap in current risk assessment practices. So, relying solely on chemical monitoring systematically underestimates the actual risk present in real-world scenarios. So we think that combining bioassays with chemical analysis allows for detection of cumulative mixture effects. It allows for identification of major toxicological contributors and for conversion of complex exposures into practical measures, such as effect-based trigger values. And what are the health impact of the chemicals mixtures we have tested, we have seen that assessing the risk of chemical mixtures in human breast milk, it suggests that there's a potential developmental toxicity concern. It's mainly POPs, PFAS, and bisphenol A that seem to be the major contributors to the risk found in breast milk based on our current knowledge. And this highlights the lasting consequences of past environmental issues and the importance of avoiding their recurrence. And finally, we confirmed that exposure to PFAS is linked to changes in newborn birth weight. However, comprehensive testing of the entire chemical mixtures reveals that these findings represent only a small portion of the broader problem, as Timo pointed out as a result of the whole mixture studies. So what tools have we developed? We have developed this chemical mixture calculator that Martin has presented. We have established effect-based trigger values for water and food and examined those for human blood as presented by Timo. And we have advanced and examined the relationship between suspect screening and bioassay testing through effect-directed analysis, with microfractionation playing a crucial role in achieving success. So to sum up here on our successes and learnings, we have got nice results on occurrence and distribution of chemical mixtures across the environmental, food, and human continuum, and have revealed how chemicals travel across compartments. We have confirmed that the additivity principle applies when we talk about low levels of many chemicals as they occur in real-life mixtures. But this is also good news, as mixture effects can be predicted then. And then the health risk I just presented. We may have a problem with human breast milk, but we do not recommend not breastfeeding, but we see a large contamination of human breast milk, and have correlated PFAS to reduce birth weight. There may be a link between phthalate exposure and ADHD. And these legacy chemicals here, contaminants, they are risk drivers and are here to stay. And the methods and tools developed, we think this whole mixture testing in bioassays combined with chemical profiling is a way forward to deal with these complex chemical mixtures. And then we have our software tool, we have the effect-based trigger values, and the suspect screening and effect-directed analysis that may be key to identify chemicals of emerging concern. What has our outreach been? It's illustrated here on this basic slide. We have established a web page and have presented news regularly there. We have prepared 4 newsletters. I cannot go through everything here. I just point out the main activities. And then we have prepared 4 podcasts and totally more than 30 videos and animations. We have a few publications and more will come in the future. And then we've been present at several conferences, SOT, CTAC, ESTIP, Eurotox, and the World Congress, to mention some of them. Then we have prepared 5 policy briefs. 3 of them are final and 2 more will come by the end of this month. And then we have had 2 webinars and trainings where we have trained the stakeholders and the public to use this chemical mixture calculator. And what are the impact on EU legislations? Our findings have implications for several regulations, including the REACH regulation on industrial chemicals, legislation for foods, for instance, the plant protection product legislation and legislation on food packaging materials, the wastewater directive, and the CLP legislation for endocrine disruptors. So we think that protecting human health calls for a transition to monitoring frameworks that consider chemical mixtures. And we advise to integrate chemical and bioanalytical methods to accurately assess the extent and effects of chemical exposures throughout the environment, food, and human systems. What are the future perspectives of our results? We think that for regulators that we need to implement EU legislation on chemical mixtures, and this is necessary, and this can, for instance, be done by incorporating a mixture assessment factor. For scientists, we advise to focus research on emerging chemicals of concern regarding both their hazards and exposure, rather than studying the usual suspects over again. We recommend further development of NAM and exposome-based methods for mixture risk assessment. And we think that establishment of effect-based trigger values for human blood should be a priority. And then a final recommendation for industry. We think there's a need for increased commercial availability of standards for emerging chemicals, because only this will allow us to identify hazards and the exposure levels of these emerging chemicals that we are detecting in the samples. So you can find more information on the website or on our LinkedIn profile. And I would greatly acknowledge this dream team here who has contributed to the success of the project. And of course, we acknowledge the EU for funding and our project officer for a nice collaboration. And then I'll say thank you to all of you for your participation today. And now we'll have a Q&A session. So please, if you have any questions, you can either put them in the chat, or you can raise your hand. Okay, we have got a question here to Sebastian. We are some partners present in the room, and I need to switch the video so you can actually see people in the room. They should be here. Yes. So the first question is: a risk driver analysis based only on target analysis? Was there also an assessment how much of the risk may be from unknowns? In other words, is this reassuring that risk drivers are already regulated and we have the right focus? Good question.
Okay, so let's start with the first part of the question. Actually, there are three questions. Yes, it was based on the targeted analysis, but also on suspect screening. For one case study, we had semi-quantitative levels from the suspect screening, which we also took into account. And for another case study, we used qualitative information coming from suspect screening, and then we used predicted exposure levels. Second part of the question, no, the unknowns, they cannot be assessed using a component-based approach, and that's a major limitation. So on average, I'd say we were only able to assess a third of the substances we have identified. So because there are simply no data, no hazard data available. So that is already a limitation, but then the unknowns, well, they cannot even be taken into account. And then third part of the question, I mean, the good news is that at least for those substances that are on the market and that we have assessed, only BPA seems to be a problem, and it's kind of a known problem, and regulation is trying to tackle that. POPs, I mean, yeah, we need to reduce those concentrations further, but that is difficult. They're not accessible to regulation. So yes and no, I would say. And also, yeah, I mean, given the results that we obtained in panoramics about the effects of the unknowns, that's a major question mark.
And I would like to add that for the PFAS, we have shown associations with risk for the known legacy PFAS. But for the big group of PFAS, we don't know if there'll be the same association to human health outcomes. And it should be a major priority for the future to either to restrict regulation of the whole PFAS group or many of them, or to make extensive testing of the PFAS. Okay, and there's a question on if the slides will be available, and we will put the recording of this meeting on the website afterwards. And then there's another question. If most of the risk of mixtures is driven by few compounds, how would you justify the math, and how you would see its use at each step, registration step, evaluation for specific uses? Thank you for the great presentations. Yes, this is another good question. Sebastian, would you like to address this? Or?
I can start. So it depends on what kind of math you're thinking of. If it's a generic math applied to, let's say, all the industrial chemicals, then I think it's not justified based on our data. One could think about maths that are data-driven, so maybe applied to substances that have a specific hazard, maybe to substances that can cause developmental neurotoxicity, and then you would apply math to just those specific substances. How would you implement that in the regulation? Yeah, well, I mean, this is a major point of discussion, because as a producer, you're responsible for your chemical, but you don't know about co-exposures from other chemicals. So it's not easy, and I don't have the answer to this question. So maybe, yeah, you have some other thoughts.
Martin, do you want to add to this?
Just a reminder, keeping the presentation about the iceberg modeling. It provided some evidence. Well, what we should always keep in mind is what we know and what we don't know. If it comes to math, and so yes, that's the implementation is unclear, the process and so on. It depends on regulatory framework and yeah, and so many different factors at the end. We should also keep in mind the regulated compounds are still present. So however we want to justify a math setup calculation, they should be reconsidered as contributor. But we have problems to regulate them. There are more or less not many options left from the regulatory point of view. So maths should not only be limited to unregulated compounds, at least the derivation of a math.
Thank you. Yes, and we have another question here. What is your experience with the different dissemination tools you used? Did you get people engaged with your research via the podcasts and the policy briefs? And I agree with Martin Scholze. Okay. Thanks. François, would you like to address that question?
Yes. For sure, we had I would say good KPI and good metrics regarding our dissemination and outreach material. Regarding the policy brief, it's not yet the case. They are the last deliverable of the project, and they will be shared and submitted next week. Nevertheless, the best technique is to engage directly with the people you want to talk to or you want to impact, and that means meeting in person the relevant stakeholders, the relevant DGs, so you have a real uptake of the message.
Yes, I agree with you. And now we have the agreement with the 0 PM platform, where we will present in the autumn.
Exactly. So we engaged recently with DG Environment to present to the Zero Pollution stakeholder platform, coordinating by DG Environment to present also at the end of this year the results of the project.
Yes. Are there more comments or questions or hands raised? Otherwise, it's time to say goodbye and thank you to all for participating today. It was a pleasure meeting you. Thanks for the good questions. Bye.